Okay, good morning again, everybody. As Heather said, thank you for coming here to spend some time with us today to learn about Pointwise and the things we have going on and things that are coming up. She's already been over the agenda. So this morning, for a couple of sessions with a break, I'm going to go through and talk about some things that are tools, I think, that are handy for working on turbine types of geometries and meshing projects. So let's scroll down here to an overview of the topics that I want to talk about today. So we're going to start out this morning talking about situations where you have gaps and strategies or tools for going through and meshing that type of a geometry and filling in the gap with a block in that type of situation. After that, I want to go through and talk pretty briefly about fillets and some tools that we have for working with fillets and topology that's handy for those types of geometries. After we cover the fillets, we're going to talk about extrusions and how you can use extrusions to develop or hopefully generate some fairly nice boundary layer topologies for bladed geometries. I'm going to talk about periodicity and how you can set that up in Pointwise. And we're going to talk about the solver, the elliptic solver that we have in Pointwise, which is one of our very strong tools, especially for structured grids. I'm going to start to finish things up later this morning with diagnostics, talking about the examine command and some of the tools that we have there that you can use with your meshing to try and find out about the quality of your mesh. And then finally wrap up with a few slides about our scripting language and resources. So the first section, we're going to talk about this gap situation. So I'm sure most of you are familiar with this or have seen this probably along the way in your work, where you have a blade situation or a blade path that you're working on, and either the shroud or the hub, in some cases, you may have a gap between the blade and the adjacent geometry. A lot of times we choose not to mesh that region depending on the focus of our analysis that we're working on, but many times we do need to mesh it. And what are the ways that you would go about trying to do that in Pointwise to make it as simple as possible? For this example that I'm going to work through, I'm actually going to go ahead and just put surface grids on the blade as a starting point and then use that to generate the topology around the base at the tip of the blade and then go in and fill in with the block. So we can kind of see the whole process as you work through that. So these are the steps that I'm going to kind of take for this first case. I'm going to go ahead and create the blade domains. I'm going to modify the domain and connector topology after I create the domain so that it's a little bit more applicable for creating a domain on the base region in the gap. And we're going to do several things actually in that step in terms of splitting the topology and changing distributions and dimensions. And then after that, we'll create the domain on the base in the gap region, and then simply just take that domain and project it across the gap to the shroud, and then fill in the rest of the topology. We may see a few interesting things along the way, though, as we go through that, and I'll show you some of the things that may come up and just the simple steps that you can take to get past those. So the first thing that I want to do before I begin my example is to go into the defaults tab in Pointwise and set up some default values. This tab in Pointwise is up all the time. Those of you that have been using Pointwise are familiar with it. I do always recommend to users to use the defaults as much as possible because it does make Pointwise much more efficient in creating your topology, especially for setting connector dimensions and having all of your topology dimensioned as you build your domains and blocks. Otherwise, you can spend a lot more time downstream trying to define those dimensions and making things add up as you need to, especially in a structured grid where you have to have computationally rectangular regions. All right. So for this example, I'm going to set up a default dimension of 101, and we'll use that to define our domains. So let me switch over to Pointwise. All right, so here's Pointwise already set up. I have our geometry already read in just as we saw on the slide, and I'll go over here to the defaults tab, and I'm going to go ahead and set up a default dimension of 101. And so since I'm using a dimension value, that means all the connectors will automatically have the same number of grid points assigned. Can everybody see the projection okay? Okay, good. All right, so now that we have this set up, let me get back to my slide. We can just use the domains on database entities command to go ahead and generate the topology very quickly. Domains on database entities is nice in that it creates the connectors and puts them together into domains or surface grids automatically in one stop, which is very quick. The tricky part about using domains on database entities when you're doing structured grids, of course, is the fact that those domains have to be computationally rectangular, which means the surfaces that you select to generate these domains, they need to be essentially rectangular. They need to have 4 edges. Otherwise, pointwise will not be able to put them together into a structured domain. That's the other reason why I use a straight dimension for the connectors instead of an average spacing, so that all the connectors have the same dimension, and of course that's computationally rectangular and can be put together into a domain. All right. So back to pointwise, I'll select my surfaces, and let me set my mask over here. So I just use a selection box to select the 2 surfaces. There is one surface for the pressure side and one for the suction side of the blade that we can pick. And then all I need to do is just come up here and click on the command for domains on database entities. Of course, I want to make sure that I'm creating structured topologies. Pointwise has defaulted to that here as a selection to create structured entities. As soon as I click on domains and database entities, I get my 2 new surface grids there that I can work with as I move along. All right. And this slide is just showing the results of that. All right, the next thing that I want to do is to go ahead and do some clustering of my grid points, particularly in this case to the leading and trailing edge, because eventually, remember, I'm going to work on that block in the gap region, and I kind of want the topology ready for the construction process at the end of this section. And so I'm going to go ahead up front and do a little work on these domains to cluster them a little bit to the leading and trailing edges of the blade. And to do that, I'm going to use this tool that we have that allows you to select spacing constraints directly on your connectors, right at the top level of the interface. And in order to select them, I have to change the settings for my mask so that I can select those spacing constraints. While we're doing this, I'm actually going to also go ahead, as it says in the last bullet, and cluster the domains towards the top and the bottom of the blade or at the shroud and the hub. Even though we don't really need that for this example, but just to go ahead and show it. All right, so here's our topology again. I still have the database surfaces selected. I'm going to change my mask now, as I mentioned, to select spacing constraints. And you can see the tooltip text there denoting spacing constraints on the mask. And so now I can actually come in and select these spacing constraints so that I can specify clustering values directly. And it's interesting to note and always keep in mind that these spacing constraints are rendered as a small arrow towards the ends of your connectors. And it's usually, I think it's supposed to be about 10% of the arc length of the connector that's represented. And so if the connector is really small in rendering in your display window, you may have to get very close to the end of the connector to actually highlight it and select it. In this case, I'm actually going to go ahead and specify a spacing constraint for all of the ends of the connectors that I have, so I can actually just hit Control-A on the keyboard to select them all directly. And you can see them highlighted in the display window. Once I have them selected, as is shown in the next slide, I can just simply go up to the toolbar and type in the new spacing constraint value 0001, which is what I want to use in this case. So my toolbar up here is a little bit pushed off to the side. I'm going to pull it down, start a new bar below the top one. It's going to take up a little bit more space, but that's all right. And since I had spacing constraints selected, of course, the delta S or spacing constraint field up here is available for me to type in. So let's go ahead and type in our new value. 0001, I hit enter. And as soon as I hit enter, the grid is updated automatically. All the connectors are distributed based on that spacing, and, my domains are now clustered the way I want them to be. All right. Questions so far?
A question?
Yes.
When you change the spacing constraints, does it use a 10H spacing to figure out all the...
Yes, it's using the default hyperbolic tangent, yep. Yes?
Is there a way just to select also span-wise connectors for the spacing? So you said you entered control A,
Yes.
all?
Yes.
But is there a way to just take the span-wise?
You can select them individually if you want to. I mean, I didn't have to select them all at the same time. So I can go through and select them individually. I could also use a selection box to select them locally as well. But yes, if I wanted to just do the span, probably I would just use a selection box and swipe it across the top and the bottom and select just those. Answer your question?
Yeah.
Okay. Anybody else right now? Okay. Okay, so the next thing I'm going to do is go through and make some modifications to this topology because, again, my ultimate goal, as I mentioned, is to generate a domain in that base region. Right now, I have a single domain that sweeps all the way up to the leading edge of the blade and around all the way back to the trailing edge as a second domain. But I'm going to need to create a domain in the gap which has 4 edges. So I'm going to try to set up my topology so that my domains on the surface are also following that same setup. So I'll need basically a single domain on the leading edge, a domain on the suction and pressure sides, and a domain on the trailing edge. So I'm going to do some splitting and a little bit of joining, and then we're going to go and do some redimensioning and distribution as well in order to get the topology that we need. All right, so this next slide goes on and talks about generating the actual domain, so we're not ready for that yet. Let me go back over to pointwise. And so I have my clustering done. Let's go through and do some of this manipulation and work on our topology. So I'm going to zoom up here on the trailing edge first, and I'm going to move my rotation point, and it's not turned on right now. Let me turn that on so you can see that. So I just used Control Shift and right mouse to move that. Of course, you can move it to any pickable point in the model. And so the first thing I want to do is split this domain here on the pressure side of my blade so that I have a nice domain essentially that kind of caps the trailing edge. So I'm going to select that domain after I change my mask. And I'm going to go up to Edit and pull down to Split. And so now I can essentially pick, again, any pickable point in the grid or the database as a split location. As I'm looking down here, I can see down here at the bottom in the status bar, very handy information. If you don't use this, this is very useful information down here. Whenever you're moving the cursor around, it does tell you where the cursor is currently located. So I can see the I and J locations, which is kind of more important to me here in the splitting operation because I want to possibly split at a particular computational line in the domain. But I also have the XYZ Cartesian coordinates for this location in space. And since this domain is created on a database surface, I also have the U and V coordinates, which can also be useful in certain circumstances where the cursor is currently located. So definitely use that as a resource as you're working on your grids. All right, so this is I equals 8 location, which I think looks pretty good for us to kind of cap off the trailing edge. So I'm going to split there, but before I do the split, I'm going to go ahead and zoom out and move up here to the leading edge and go ahead and define a split up here as well. And let's, I don't know, I think 88 or 89 looks pretty good. And then I have my 2 split locations defined. I can do as many splits as I want in one pass, but this is all I need for our case, so I'll just click OK. Pointwise goes ahead and splits that domain, so now I have 3 where I had 1. There's a domain on the trailing edge, and I have just 1 here at the leading edge. I'm going to select the other domain and go ahead and split it as well. And since I was about 13 into the interior from the other side, I'm going to go to I equals 13 on this side as well. Define my split location, click OK. And so now I have these 2 domains here, which are more or less on the leading edge of the blade that I'm working on. All right, so a few more things to do here. As we move on, ultimately my goal is to get these connectors defined in the gap region that I'm working on, but I'm going to join these domains together, make sure my distributions look good, and then we'll go ahead and create that domain. All right, so I have these 2 domains already selected, so I'm going to go to Edit and Join. So now I have a single domain here. If I wanted to, I could have gone ahead and joined the connectors at the top and the bottom at the same time. I didn't have them selected, but I could have done them all at once. I'm going to go ahead and select those connectors now and join them together as well. We'll just use the little selection box here to select these and hold on to the Control key. Select these 2 up here. Again, Edit and Join.
What is the point of joining them? Could you just leave them separate if you want?
I could, yes. I could leave them separate. It's a habit of mine working on structured grids to, when I'm defining structured domains, if it's convenient to just have 4 connectors, but it's not necessary. Yep. Good question.
Sorry, but now
yes.
the new joint connectors, they have now some internal breakpoints.
They do have some internal breakpoints, and I'm about to go fix that. That's a good point. Yep. Yep. Pointwise is always going to try to preserve distributions of connectors. So when you join connectors together, if they're dimensioned already, it should apply breakpoints automatically on the interior of those connectors to try to preserve the distribution that you already had. But you can remove those, and I'm going to do that next. Any other questions?
I built a little script to join them and get rid of the breakpoints. Perhaps if you journal it, scripting when you do the join, it doesn't keep the breakpoint. So it's automatically clean if you journal it. Yeah. So I have a little utility script to do that. It's very easy to create.
That's a good idea. That's a good use of a script, utility script.
Yeah.
Yes?
Is the splitting domain only for the structured domain?
It's currently only available, yes, for structured domains. But that's going to change, I think, in the next version of Pointwise. I think we're going to have the ability to split unstructured as well. It's a good question. Any other questions right now? Okay. All right. So let's go ahead and look at these 2 connectors that we joined. And I'll just look at my list real quick. I do have 2 connectors selected. I'm going to go to Grid and Distribute. And I'm just going to click on over here to the Breakpoints tab. And actually you can see in the display, as soon as you get into the breakpoints tab, it does show this square on the interior. There should be one on the other connector as well, which is out of our view, and that represents a fixed breakpoint location as opposed to an arc length breakpoint location. So fixed locations are simply where the connector already had a control point, which is the point that defines its shape. That's the difference between a fixed breakpoint and an arc length breakpoint. All right, so we don't really want any of these interior breakpoints. I want my connector grid points to flow freely along the length of these connectors, so that's why I'm going to remove these breakpoints. That's it. The other thing that I'll go ahead and check here real quick for these connectors, since I did some joining and splitting of domains, is just to see what their dimension is. They both have 26 points, of course, because they're at the ends of a structured domain, but I need to make sure I match that at the trailing edge of the blade so that I'll be able to create my domain in the gap. All right. Let's zoom back out. And I'll move my rotation point back here to the trailing edge again and just rotate around. So we want to have the same dimension back here. Select this connector. And if I use the dimension option that I have here on the toolbar, which is available, and change the dimension of this connector, since it's a structured domain, the grid points on the interior will vanish on me because it'll be unbalanced. So when I'm working on structured grids, I generally, most of the time, I'm going to want to use the grid dimension command, because when you're in that panel, Pointwise will work to preserve your topology for you in a structured grid. It doesn't do that when you're using this toolbar option. This is just a straight dimension. Any connector you select, no matter whether it's in a structured domain or a structured block or not, it's going to go ahead and change that dimension immediately. And in this case, the domain would be emptied, and it would say that it was unbalanced in the list tab. All right. So instead of doing that, I'll go to Grid and Dimension, and my connector here selected. I should see the other connector highlighted as well. Up at the other end, you can see it's rendered in a hot pink color, indicating that it is also selected. It's a little bit hard to see there, it's small. I can come down here, type in a new number of points, hit enter, and dimension. And so now my dimension here matches as well. So really the only thing I have left that I want to do, since I have changed the dimension of this connector, that means my distribution of points here is going to be a little bit finer at this trailing edge. And so what I want to do is bring some grid points down on the domains on the pressure and the suction side to kind of match that distribution a little bit better. So I'm going to change again the spacing constraints to do that. Let's go back over here to our mask after we get out of the dimension command. Spacing constraints. And the first thing I'll do is just kind of highlight and look at this connector just to see what's going on and see what the value of this spacing constraint is. And I'm actually just going to copy it and apply it on the outsides to these attached or adjacent connectors. But the first thing I like to look at here is just to kind of see what the status of this connector's dimension or distribution is. And seeing that this value is in parentheses lets me know that this is a calculated value by Pointwise. There isn't a value that's already been specified by me specifically for that end of the connector. And so more than likely, if I go to the other end and see that it essentially has also the same value and it's also in parentheses, then I know immediately that that connector has an equal spacing along the entire length. So it hasn't been constrained in any way by me, and the code hasn't done anything to the connector to constrain it either. All right, so I'm just going to pick one of these spacing constraints. I can hit Control-C on the keyboard to copy it. And you'll see down in the messages, copied one spacing. So I'm ready to apply that. So I'll come over here and select the spacing constraint on this side, and I'm going to go ahead and select this one as well, and also at the other end of the span. And holding the Control key, I'll select those as well, and then Control and Shift and V is a pasting operation that's specific to spacing constraints. So for most edit and copying operations and point-wise, you just do a Control-V to paste, but if you're pasting spacing constraints, it's Control-Shift-V. It's probably on your mouse pads that you've got in front of you. All right. So we should be in pretty good shape. This is our gap region up here where this surface is being rendered. I think we've got just about everything set up that we need. I'm going to go ahead and change the rendering of this surface. So that we can see through it, and I need to, sorry Travis. I'm rearranging your, all right, I'm going to change that to a wireframe so we can see through it. All right, so this is my gap area. I've just made the surface outline so that I can see through it. So I'm pretty much just about at the point where I'm ready to go ahead and create this domain here at the end. So let's go ahead and switch our mask and see what we get. I'll just go ahead and select these connectors. Have 4 connectors selected. But even without going ahead and clicking on a symbol on the toolbar, I can see that I have an issue. It's not computationally rectangular yet. Because I split those domains, I can see that I have some dimensions that are out of balance here on the pressure and the suction side. So I need to go ahead and adjust that before I can assemble it. I'm going to go ahead and use the larger value, which is 89. Select my connector. Again, if I do it on the toolbar here, I'm going to break my domain. So I need to either select both of these connectors or use the grid dimension command. I'll just go ahead and select them both and do it on the toolbar. 89, hit enter. My domain hasn't vanished, so I didn't break anything. And instead of selecting these connectors individually the way I did the first time, I'm going to use a selection box this time. I hope most of you know you can use a selection box at any time by just dragging your left mouse, the default mouse setup, and you'll notice that the cursor has a little box with a line that overlaps. That basically means anything that touches the box will be selected according to your mask setting, and my mask right now is set to select only connectors. If I hold the Shift key down while I'm using a selection box, I can change the selection style on the fly. So now the cursor has a little dash that's inside the box. So that basically means only things that are entirely inside the box will be selected. So I'm going to do that to try and just select these connectors at the end of my blade, which is convenient. It looks like my dimensions all match up. So we'll just come up here and use the Assemble Domains command on the toolbar. And I'm still out of balance.
Yeah, 26, 29.
Yep. So I still need to redimension that other connector. I set it to 26 instead of 29, so let's go ahead and change that. Sorry, I'm trying to lose my voice here for a little bit. All right, so we'll go to Grid, Dimension. I'll select this set on the trailing edge again.
When you change the dimension on a connector like that,
Yes.
and say you haven't specified any spacing constraints, does it make all new spacing constraints at the end of the connector, or does it try to preserve what you had there before?
As long as it's still set as a hyperbolic tangent, and you haven't and you haven't set any spacing constraints on either end, it'll just go ahead and give you another equal distribution of points. But if it's a hyperbolic tangent and you did specify one or more of the spacing constraints, then it'll maintain that even after you change the dimension. Yes?
Before you copy the spacing to the neighboring domains, do they automatically change? Or?
They do not. And so in this case, I would normally want to go ahead and update those again, or make sure I had the dimension right the first time. Yeah. So we could do that now. Yeah. Any other questions? All right. Okay. So let's go back and select our connectors again. Get back out of dimension command. My mask is still set. Looks like my dimensions match. Symbol domains. Get a new domain. Looks like my distributions have worked out pretty well. Of course, since I'm putting an H-style grid in a rounded region, I get these somewhat skewed cells up here, and what are the corners, what will be the corners of the domain. So I can use the elliptic solver to smooth that and pull those corners out a little bit and make them a little more rectangular, which would be nice. I'll go ahead and change the mask real quick and select the domain and just go ahead and run the solver just using the default settings. Looks better. All right, so we have our domain now. Let's go back to the slides and see what we have here. So this is basically where I'm at right now. We did all that work on the topology to kind of get it ready for this. Obviously, I could have at the very beginning of this section just come in here and created these connectors in the gap and just created a domain and gone on. So I've done a little more preliminary work than what we really needed for this block. But just to kind of show some of the tools and some of the things that you have to keep in mind as you work through it. So we already ran the solver on this domain to pretty it up a little bit. It looks better after I assembled it. So now we're ready to go through excuse me, the process of creating a new domain across the gap on the shroud, and then simply going through the steps to fill that in. So what I want to do is copy the domain that I have. I can just use Control-C on the keyboard and then paste it. That'll put us into the paste panel where we go through and select what we want to do with the copy. In our case, we're going to use a projection to project it onto that shroud surface. Okay. And this next slide, the slide I thought I updated, so there's a little bit of difference here between the slide and what we're actually going to do. So for the domain and the domain's connectors, I'm actually going to use this top option, project points, and not project shape. There's an interesting difference in this particular case. I'm projecting the domain with its connectors, and when I use the option to what's highlighted here, project shape is intended to essentially just take the shape of the connectors, put them on the new surface, but maintain the spacing constraints that you had on the original so that it doesn't give you what we call a type general distribution after the projection. The interesting thing about this example, though, is that when I use project shape, because the change in the connector is significant enough and the domain that's going to be on the shroud is actually initialized. So instead of preserving the elliptic solved or elliptic solution on the domain that I have that I'm projecting, it actually updates it and initializes it. Of course, after that I could run the elliptic solver again on the copy and make the match. But in this case, I'm actually going to use project points because that ensures that the interior and the connectors on the copy are going to match after the projection. All right, so let's look at that. So that's, when you get your notebooks, if you remember, you may want to go back and make a little note on this and circle the other option. All right, so my domain is still selected. I can just copy it with Control-C on the keyboard, Control-V to paste it. And as I mentioned, that puts us into the paste panel. We have a lot of options of things that we could do to this copy if we wanted to. It's important to remember when you're pasting a copy of an object, you can actually perform multiple types of transformations on it at once before you actually save the results. All we want to do here is a projection. So I'll click on the project command. And so most of the things that I want to use are already selected. I don't want to do the interior only. I do want to project the connectors as well. And as I mentioned, I am going to use project points for this example. I also want to come down here and select a target database for it to project onto because the copy, the original domain, is actually already on a database surface. You'll have noticed that it was purple when I selected it. You'll also notice that up here in the table it already says that 100% of the points are on, and that's because where it's located it is on a database surface, but I want it to move across the gap to the shroud surface. Okay, so I'll just rotate around a little bit so we can kind of see a slightly different view. I'm going to turn off interior only. I'm going to click on Target Database Selection, Begin, select this surface which represents my shroud in this example. Click on End to end the selection process. You can see the projection vectors that are rendered on the domain that's being projected in green. And then we just click on Project. And again, after the projection, it does say that 100% of our points are on. So it's transferred all of the connectors points and all the interior points of the domain to the shroud location. And we can zoom up here at the leading edge, for example. And this is one of the nice features, I think, in Pointwise about doing projections for domains and connectors is that you can always see your original entity as well as the copy that's being projected, so you can see what the differences are, and you can tell usually pretty immediately if it's performed the way you expected it to or the way you wish it to in projecting it onto the database. All right, let me just zoom back out here and zoom up on the trailing edge and make sure it also has transferred, and it looks good. All right. So we just click on OK to save that. And as I mentioned, we can perform other transformations on the domain copy if we want to, but I'm happy with this. Click OK. The original domain is still selected, but I now have a new domain available. All right. So to finish this process, we really only need to go in and just create some connectors and create domains in the block, in the gap, and we're pretty much done. So to do that, I'm going to come back over to my Defaults tab. I'm going to type in a new dimension. Only need about 5 grid points to span this gap on these new connectors. So I hit a new default dimension of 5. To make things easy for me to select to create these new connectors, I'm just going to turn off the display of my domains temporarily, because when you're creating new connectors, all of these points on the interior of these domains are pickable locations, and so I could accidentally pick an interior point instead of a node, and I don't really want to do that. So I'm going to use Control F3, which is the accelerator for turning off the display of domains but we can also turn off the domains if we wanted to. I don't really think I need to bother with that for this. All right, so I'm going to use the 2-point connector command. I've had my default already set, and just come through and click on these nodes. Definitely want to make sure that I have what we call the bullseye cursor here available, which indicates that I am mousing or hovering over a pickable location, so I know that it's found that node at this location. So if I click the left mouse while I have that cursor, I should pick that existing point rather than creating some new point in space. I'm going to move my rotation point here. Let's rotate around a little bit. Do the same up here at the leading edge. So I have all my new connectors. Click OK. So I know the domains, the domain on the base and the domain on the shroud should essentially have the same dimensions since it's a copy. All the new connectors have the same dimension, so everything should be dimensionally balanced. I should be able to create the new domains in the block now. I'm going to go ahead and create one of these domains by hand. So change my mask back to selecting connectors. Zoom out a little bit so I can get back to the trailing edge. Holding the control key. So I have 4 connectors selected. Symbol domain. One domain is created. I have my domains turned off still. We'll hit Shift or Control F3 to turn my domains back on again. And so actually, if I want to, I can create the rest of this topology pretty quickly. Just using a selection box and just telling it to create the rest of the domains in the block. So I want to make sure I have my mask set so that I'm selecting both domains and connectors. So I turn both of those on, and I'll use select in box again like I did earlier, and just kind of swipe it around that cap or region where the gap is, and come up and click on blocks, assemble blocks. And you'll see in the messages window down here that it says it created 3 more domains. In the process, there was a couple of connectors it didn't really need for that, and it created the block. So I have a new block there. So, one last little interesting thing here to look at before we move on to our next piece. These domains don't look so good. Can everybody see that? It looks like the grid lines kind of span all the way across the gap. There's no interior grid lines there. Anybody have any idea what's going on there?
There's no database.
Well, there is a database.
But it's not the correct.
But it's not the correct one. That's right. So these, because of the way the domains connectors are defined on the top and the bottom on either side of the gap, these connectors have the highest percentage of points defining the domain, and because there's sufficiently enough points database constrained, PointWise thinks these should be database constrained domains. And so it takes one of the surfaces that it finds that these connectors are constrained to and says, okay, this domain actually should be on this surface. And so what's happened here is all the interior points of these domains have been placed onto this surface, which is not what we want, but you will see this happen occasionally. It's a feature that's in there to generally make your life easier because it will automatically make your domain's interior points lie on their database surface. But occasionally a situation may come up like this where they're not really supposed to be on the surface. So we can fix that using the solve command. I'm just going to come over to my list, and I'm going to go and expand the domain portion, and should be these last 4 domains. And I can see that they pretty much all look the same. And let's go up to the grid solve command. And under attributes, we will see that, of course, since they are purple, purple indicates that they're parametrically defined. Up here under initialization, it does say parametric fit, and their surface shape is database. And these domains don't really have a database surface. They should really just be standard TFI free domains. So I'm just going to go ahead and switch that real quick. Standard, free, go back to the Solve tab and just click on Initialize. And now they look more like they're supposed to. Okay. Does anybody have any questions?
In this case, the two surfaces match. So the projected one is exactly the same as the original one. But if it's not the case, for example, the projected one is larger than the original one, then you may have curvature problems if the surface is free.
Are you talking about the surface you're projecting onto is larger?
Yes. Then these surfaces, these grids, are not exactly orthogonal with respect to the original one. So you may have curvature.
Right.
So it's not better to generate a Kunz patch or a different database there?
Around the sides of the gap?
The sides.
It could be, yes. In that case, you may want to, yes, and have a database surface there to control the shape.
So that's probably better if the surfaces do not match.
It could, yes, it depends on the topology, but in the situation you're describing, probably it would be.
Okay.
Yep. To generate your own surfaces, yes. Yes?
Would it also possible to extrude the first domain towards the second database and then project the last the domain you got to the database?
I'm not following you. Sorry.
If you have your domain on top of your
On the blade.
on the blade, can you also extrude that domain
Oh, extrude it.
to the database, and then you can also project
The final front.
yeah.
You could.
You need to make the 4 connectors manually. You have all at once.
There's several things attached to that may make it difficult. One is you'd have to determine the distance between the two, and in this situation our gap is essentially equal all along the tip of the blade. In a lot of cases it may not be, and so when it would extrude out, you may have one end of the domain that's really close to the shroud, but another end that's not very close. So that could be a possible issue. The second issue is when you're doing extrusion, you wouldn't really probably be able to use normal extrusion or hyperbolic extrusion because the front is going to change immediately as soon as you start doing the extrusion. However, you probably could do a path extrusion. So I think if you really wanted to try that, probably what I would do in this case would be to do a path extrusion. Create one of these connectors, like this one. Extrude this domain using this as a path so that the topology of the front's really not changing. It just follows the path and stacks layers. And then you could save that, and like you said, at the end, you could project that final domain to ensure that it's actually on the database surface. Hopefully it's close enough that you shouldn't have any problems with the distributions of the side connectors. One of the other things that I should point out is when you do that extrusion, these connectors along the sides will have what we call a type general distribution. So they're discretely maintained. They're not using hyperbolic tangent. There's not a mathematical function, essentially, that describes their distribution. So if you did that projection and you came back, if you did the extrusion and you came back and projected this final domain, if the change was enough that it pushed made one of these connectors shorter than it was, then you would actually probably end up with a fold in the connector after the projection. So that's something else that you'd have to keep an eye on. But I think if you wanted to do that, you probably a path extrusion would be the best, and then do the projection on the final front. John?
To avoid the fold in those side connectors, you just extrude it one step, and then you don't get any internal control point.
Just do, yeah, have the path just...
Do one step extrusion, project it, and then redimension them at once. You've done the projection, and then it should be okay.
There's no interior points in the, yep, that's true. Good point. Thanks, John. Any other questions right now?
Yeah.
Yes?
Concerning the projection, if you want to project, for example, a connector to a database surface, we have the option closest point. Which other options are available?
For projection, you have several different options. There's closest point, there's linear, cylindrical, and spherical. So let's switch back over and click on OK to save that. Just select one of these connectors as an example. So these are your projection options. Closest point is always selected by default because it generally, we find most of the time, gives you the best results. Essentially, closest point goes through and looks at every point, grid point along that connector, assuming that you have the projection option chosen to project points. It'll look at every point along the length of the connector and try to find the closest location of any database surface if we haven't picked a target that's available. And so a lot of the times when we do projections, the points typically are fairly close to the object that we are trying to project to, and that's why closest point is the default. Linear, on the other hand, can be very useful or very powerful in a lot of situations. Particularly, I find when the object, whether it's a connector or a domain that you're projecting, is significantly displaced from what you're projecting onto. And even more so if the surface you're projecting onto is highly curved, because closest point, again, tries to find the closest point on the surface to what's being projected. And so if it's a highly curved surface, that point may be over here, whereas we may really want this domain to kind of keep its shape as we project it onto the database. So in that situation where it's highly displaced, I would more often probably use a linear projection. And linear projection, by default, initially will set up with your view orientation as the vector for projection, but you can manipulate that and alter the vector however you need to. The other two options are cylindrical and spherical. They operate exactly the way they sound. Cylindrical, you define an axis about which rays are passed or out of the axis or into the axis, but perpendicular to the axis. And all the points pass along those rays, and wherever they strike a surface, they'll end up on the database. These two methods are really probably mostly useful for situations where your database is cylindrical or spherical that you're projecting onto. For instance, a fuselage of an aircraft or the body of a rocket or a missile or something like that. That's cylindrical.
Okay, thank you.
You're welcome. Yes?
Is it possible to convert a free domain to make it database constrained afterwards? Get linked when I created it free in space so that it tell them you are actually on the database.
Well, you can use, if it's not actually occupying the same space, you can use this projection tool to project it onto the database surface that we've seen. After you've done that, and for example, this one that I've just done, it knows automatically at that point that it's supposed to be on the database. So it actually does become associated to the surface. Generally, when you use a projection to do that, it will know that automatically. And in fact, if we look at this domain in the solve command, we'll see the attributes set up for it by default. So it's already trying to use a parametric method to initialize the interior. It's database constrained for shape, and it already has one database surface selected by default, which we can assume is the shroud surface that we projected onto. Okay, we'll switch back to our slides here then and move on. So the next little topic I wanted to talk about was fillets. This is kind of mainly to show you just a few script utilities that we have for trying to accelerate. John mentioned earlier a script that he has for working on connectors and their distributions and getting rid of breakpoints. There's a lot of things you can do with scripting, and I'm not really going to spend really much time other than just kind of a brief slide at the end of this section, because Travis is going to help you out with scripting later today. So in this section, I just want to show a couple of things, mainly the topology to set up for the situation that you may run into. A lot of times we don't have fillets. The example we looked at before didn't have any fillets, but a lot of times in a bladed type of geometry you may have fillets that you need to mesh. And for a structured grid, we found that trying to generate a little OH topology in this fillet region will give you a really nice topology. It's easy to work with, and we do have some of these tools that will help you generate the topology fairly quickly. I think I covered all this. It matches well, and you can create it by hand, but it takes a little bit more effort. So there's a script that we have that's available on our scripting exchange, and I have a slide at the end of this section that gives you the URL for our script exchange or our script depot. But you can use the script called fillet.glf, and you can come in and select connectors that we already have on our geometry. And essentially what it'll do is come in and split the connector and then offset from it a little bit of topology that allows you to quickly create an OH style of topology. It requires a single connector to be used. In other words, every connector that you select is going to be transformed into this type of topology. Once you have those connectors set up, you can use some of our transformations to come in and copy and translate and either stretch or possibly scale, or you can use another script that I have on here that I'll show you. It's called squeezecon.glf. So let's go ahead and read in this example and just look at it briefly. So this is the topology and geometry that we saw on the slide, and so I have a bunch of surface grids that are already set up in here on this particular piece of the geometry. 3 domains, one on the top, 1 domain in the fillet area, and then a small domain down here at the bottom of the curvature. I can come in and select these connectors after I change my mask. Hold the control key and go up to script and execute. So I just selected the script and clicked on run, and so it immediately took these connectors, split them, offset them, and created the rest of this topology automatically. Of course, it's really coarsely dimensioned, but it's easier to visualize what's happened here with the coarse dimensions. And these offsets, these domains have been offset in a perpendicular fashion to the local surface or geometry. So it does a really nice job. And as I mentioned, you can go through the time of copying some of these connectors that we have at the top and the bottom to fill in the rest of this topology, and go through the process of translating and then scaling it, but you have to go through and calculate a bunch of numbers and coefficients, and so that's already been done for us with a script. So I'll select this connector here on the top, for instance, and we'll go up and execute this other script, which is called squeezeCon. Squeeze is the connector to fit 2 endpoints that we select. So when I execute this particular script up here in the script panel, it says select the first point. It has the weighting cursor, but this is actually a cursor that I can use to select nodes with. And so I'll come down here, zoom up a little bit, and select this node here and the one at the other end. And after a couple of seconds, it takes that connector, it copies it, it translates it to the first point. It automatically calculates the scaling coefficients and scales the connector to fit to the other node. So it's a really nice utility. All right. I can just use Control E to go through this process to re-execute that script. Zoom up a little bit on that one. And so, just using that script there, I've created a pretty good bit of topology here in this fillet region fairly quickly. Right now I only have connectors with domains at the ends. If we want, we can go ahead and try to fill in the rest of the topology. The one thing that I do need to modify to create blocks from this set of topology is to take this original fillet domain and just go ahead and split it so that it matches the topology at the ends. And then we can assemble what's left. So let me switch back to selecting domains. Select that domain. We'll go back to our good old friend that we've used earlier, the edit split. I'll select this point where the node is. It's not splitting in the correct or the desired computational coordinate, so I can switch that here in the panel. Looks good. Click OK. Domain is split. Sorry. So now I have all the topology here. I can create blocks from this. So again, I can use a selection box to select all this topology. Make sure I'm creating or selecting connectors as well. I'll use the Shift key and size out a box here around the topology. Symbol blocks. So the assemble block command takes all those connectors, tries to create any more domains that it can create for you automatically, and then takes everything from that process and the original selected domains and tries to create blocks. So here it created 6 domains, and from this topology that I had, it created 2 blocks. And we can look at those real quick. I'll just change to block selection and highlight these blocks, and you can see what I have is my little H block in the middle and one little O that wraps around it. So I think that's pretty much it for that example. It's a pretty quick one. Does anybody have any questions? Yes?
Is the OH geometry always generated in the same plane as the original connector?
Yes, it should be. That's the intent.
And what happens if the original connector is not attached to any database?
It doesn't necessarily have to be attached to a database. It just calculates the plane that the curve lies in.
Ah, okay. And if it's a straight line?
That's a good question. I don't know the answer to that.
Okay.
Just another question.
But I'll find out.
The automatic meshing procedure for a block, does this also work if you have a more complicated geometry? For example, if you could create a block, but this would consist of about maybe 100 surfaces.
Domains?
Yeah, or, sorry, domains.
Mm-hmm. Does it work? Yes. It'll try to. So it depends on the complexity of the topology. If you took a simple cube block, but it was made up of 100 domains, you'd probably create that fairly easily. If you have 100 domains that make up 20 blocks, it'll try to do that, and it may take it a while because there's a lot of permutations that it has to go through to find the paths of all of those surface grids and figure out if they're closed or not. So generally what I recommend is to use this automated assembly as much as possible, but be selective in your use. So I wouldn't build a grid of hundreds of domains that would make up hundreds of blocks and then try to tell pointwise to assemble all that, because you'll want to get some coffee and come back tomorrow because it will take it a while to do that. So just select, be selective and have it do pieces of the topology at a time, and it usually is very successful. I'm often amazed at the complexity of topologies that it will assemble automatically. But it does always strive for the simplest case as well. And this doesn't affect structured grids as much as unstructured, where you may have situations where unstructured domains and blocks have holes in the interior. So if you had, for instance, just the simplest case, a couple of nested spheres, an outer and an inner sphere, if you go in and choose that just on the face of it, it's going to want to make 2 blocks out of that. But we do have tools in the assemble special command that allow you to give it a little bit more information, and it'll try and figure that out for you automatically. So it depends on the case, I guess, is the answer. But assemble for structured grids, I think if you use it selectively, like I said, you'll have a lot of success with it, and it'll create your topology pretty quickly. Okay. Any other questions? Yes?
The middle there, I think it was the squeeze con.
Yep.
You made, is that chosen arbitrarily, or as a function of some input, or does it? How do you adjust the quality there? Because you could maybe have some very bad cells right at the junction there.
So
Or OH.
the script itself, what it does is I pick the connector that I wanted to copy, and then I pick the endpoints of its new location. Okay, so the first point that I picked is kind of like the anchor or the translation point, and so it translates it, and then in the script it actually calculates a scaling factor to scale that connector to the other endpoint. The distribution in this case works out pretty well. Obviously, if you had a situation where you're starting to scale or squeeze that connector to a much larger arc length or a much smaller arc length, then you may end up with some skewing in the grid.
Then you have to use a solve or something. Or
It depends. We're going to talk about the solver a little bit more later, but it really depends on the topology, because a lot of times issues with the grid and skewing can be because of the distribution on the connector itself. And so you want to make sure the connector's distributions are all fine. Like a few minutes ago when we were talking about doing an extrusion and projecting the final domain, you could end up with a kink in a connector. Those sorts of things you have to be careful about. But generally, yes, if it's an issue in the interior of a domain, the solver will very often clear it right up. Yes?
This example you generated 2 blocks. There's no danger that the third block that will comprise the other 2 blocks will be generated.
You mean that it may have just generated 3 blocks instead of 2 in this case?
Yes.
It's possible. Like I said, it does strive for the assemble command strives for the simplest topology usually. You could create 3 blocks from this if you have another domain that runs down the center between the two. If I created another domain that spans down the center of this, then I could create 3 blocks easily, and it would be okay. That's a valid topology. We don't really need it.
And what's the minimum number of domains that you need in order to use this for example, if you have a channel that is in cross-section square, you need one domain to generate first, and then
You can start with only connectors.
only connectors, no domains at all. Okay.
Assuming you have enough topology and that it's all dimensioned properly.
Yeah, okay.
You know, that everything matches computationally. Yep.
So the domains will be generated
First,
domains,
yep.
and then automatically, and then the block.
Yep, it's a real time and saving feature. Yep. Next thing I wanted to talk about is extrusions. And this is going back to the geometry that we were working on in the first example case. And in this particular case, I don't actually have a gap between the blade and the shroud, so this is a slightly different geometry, but essentially the same. What I want to do is just come in and extrude an O about the blade, but it's specifically in this case, the reason I wanted to show this was just to make sure everybody is aware of the boundary conditions in the extrusion tool that allow you to constrain boundaries of the extrusion to database surfaces. So that's kind of the main intent of this example. So starting with this geometry, I'm going to go in and set up some defaults like we did before, same dimensions, but instead of changing the spacing constraints and clustering after I create the domains, I'm just going to go ahead and set that up as a default and let Pointwise do that automatically as it creates the connectors in the domains. And then we will use the onDatabase entities command again, as I did earlier, to create these two domains. So let's go ahead and look at that in Pointwise. I'm going to click over to my defaults. I actually saved this file with the defaults already set. So dimension 101, beginning and ending spacing constraints of 0001. So this essentially means at the beginning of every new connector and the end of every new connector, those spacings will automatically be applied, and then the domains will be created and they're already clustered for us automatically. All right, let's change the rendering of these real quick. All right, so there's our new domains. All right, so what we're going to do is go in and set this up for extrusion. So we're going to extrude both of these domains away from the blade, but at the same time, we want the ends of the new block to be constrained to these surfaces. So we'll use the database surface BC, or database constrained BC, for the extrusion. So what we want to do is select the two domains and go to the Create menu and choose Extrude Normal. And then I said in the slide here we can just click on Done to go ahead and use the default face setup, and we'll do that, but I want to talk about this a little bit more after we look at the example. All right, so I'll select my domains again, go to Create, Extrude, and Normal. Oops. And this first tab always comes up whenever you have more than one entity selected to extrude. And so what happens is Pointwise, since we have domains selected, tries to assemble those domains into as few faces, initial faces for the extrusion as it can. Very often this is fine, you may be happy with it. And in that case you can just click on Done, and that takes you to the regular extrusion run tab, and you can move on and set up your extrusion. Likewise, if you have connectors selected that you're extruding into domains, if you have multiple connectors selected, it's going to automatically put those connectors together into as few loops or edges as it can to perform an extrusion. And again, you can always go ahead and accept what it's set up, or you can change that. And we'll come back and look at how to set that up first. But let's do the example as it's talked about in the slides first. So I'm going to click Done, and that puts us into the Run tab for extrusions. And so what we want to do is set up the boundary conditions. I'll do that first. And so I have a slide here showing setting up the BC. So let's click back over to pointwise, go to boundary conditions. We're in a mode now where we can select specifically the boundaries of the front that we have. And for this particular case, the front is essentially this shell of domains that wraps all the way around the blade. And so either at the trailing edge or at the leading edge, there is a connection where we're going to have a branch domain after the extrusion. I didn't really pay attention to that because I had just accepted what pointwise gave me for the face. So the only boundaries are going to be at the shroud and the hub, and that's where I need to set up my BCs. So I can use the selection box if I want to select this. As soon as I have that boundary selected, my boundary condition type pull down is available. It's defaulted to display, which is what is always the default for hyperbolic extrusion. I can pull this down and we can see our second option here is database constrained. As soon as I click database constrained, the panel changes and it gives me the ability to select database surfaces that I will constrain that boundary to. So this is kind of like the target selection that we just saw in the project command. Click on begin. I'll select this shroud surface. Click on end. And very importantly, for those of you who have been using pointwise, you probably already know you have to make sure you click on this button, set boundary condition, for it to be enforced, or otherwise it'll just forget about it if you change to another tab. So I'll click on set boundary condition. You know that the BC has been applied when you see these little ghost points rendered around the edge of the boundary or along the edge of the boundary. So this indicates that the BC has been applied. You can select the other end at the hub. Database constrained. Select the hub surface, end, set. So now both of my BCs have been specified as database constrained. So each has been set to a different surface. And that's what we see in this slide. I have a little smaller image down here that shows the BC rendering. All right. So just a few other things that we want to set up for, this is a pretty simple example or straightforward example, but I want to set up an initial spacing which is actually going to be the same value that I used for my clustering on the domains. I'm also going to go ahead and change the volume coefficient down here under smoothing to 0.01. Volume smoothing is used to try to make the volumes of the cells that are extruded equal in value. So as the extrusion proceeds, it's trying to make all those cells have the same volume. It's a fairly aggressive, a fairly quick smoothing, and so sometimes it can actually change the front so quickly at the beginning of the extrusion that the extrusion may fail. And you may find a lot of cases where you may want to reduce this volume smoothing to a much smaller value to start. All right, so let's switch back over here. I'll go to my Attributes tab, Step Size, 001, Smoothing, 01, and then the last thing is just to go back to the Run tab. As I mentioned, we'll just do 15 steps for this extrusion and click Run. All right, so back up to the top, Run tab, 15 steps, hit Enter, and Run. And it sets up the extrusion, and we can see down at the bottom our progress bar pops up. We actually have a multi-level progress bar, so in situations where you have phases, the phases are at the top. The progress of each phase, or the overall progress in this case, is shown on the bottom. And the top bar for extrusions is always essentially just the number, the current extrusion level and the total. So it takes it just a few moments to extrude out these layers. And then we can click on OK to save that as a new block. All right. So we have a new block here about the blade, but more importantly, while we did the extrusion, we constrained these domains that it's created through the extrusion process to lie on the shroud and the hub. And so if I look at this edge on in the display, let me pull this down here. We can see that these points are in the plane or in the surface and constrained, which is nice. And we can also verify that by using the examine command. We'll talk about examine a little bit more later on, but this is one of my favorite commands just to make sure that my domains are constrained when I expect them to be, or associated to the database surface. Okay, so as I mentioned, I was actually going to go back and look at that assemble portion of extrude real quick just to make sure everybody is familiar with how that works. So let's close out of this. I think that was it pretty much. I just showed these two things. So let's go back in here. I'm going to undo the extrusion, select these two domains again, and go to create and extrude normal. And so again, here's this assemble tab that we have. And if for whatever reason we don't really want to assume the face the way Pointwise has set it up, we can just come down here and expand this frame that says assemble special, which gives us control over the assembly of the initial face. There's no face active. Let me pull this out a little bit so we can see it a little bit better. So since we already have a face here, if we're not happy with this, we can come in and just tell Pointwise to delete all the faces. If I had a situation where it had set up multiple faces and I wanted to be more selective, I can of course select individual faces to delete them and not do all of them. But I'll delete all the faces here, and one of the options that we have in this panel is to just tell it to use either domains once or not, which basically means each face will have a single domain. I can also come through and select these two domains to build a face, and since these two domains selected together have two places where they can be attached or joined, Pointwise gives me the option to choose how they're put together. So this is where you have the opportunity to determine where that branch domain will be after the extrusion is finished. So you basically tell Pointwise where you want it to be linked. It's showing me this highlighted connector here at the trailing edge. So this is link 0. It's kind of rendered it up here in this display as well. But if I choose this and say use selected link, that just simply means the face is combined at this location and my branch will end up being at the leading edge after I perform the extrusion, or vice versa. So, and you can also of course develop fairly complex faces with this type of setup. In the 2D area, where this comes up a lot is when you're trying to extrude, for instance, a domain or domains around an airfoil. In fact, we have a tutorial for creating a domain through extrusion around airfoil geometry. In the tutorial, we just take the default setup for the initial edge of that extrusion, but there could be situations where you want the branch connector to be either at the leading edge or the trailing edge of your airfoil after the domain is extruded, or maybe both. So this assemble special tool here gives you the opportunity to control how that extrusion front is defined. All right. Okay, so the next topic I wanted to talk about is periodicity and how to set that up. Many of you may already have seen this or used it, but I just wanted to make sure that you're aware, because in these types of geometries that we've kind of been focusing on, bladed type geometries, periodic boundaries are very often used because they're such a cyclic type of geometry. So I have an example that we can go here, and I think this will probably be the last thing we'll talk about before we have our break. So we'll have a break in just a few minutes. To create periodic entities, you use the create periodic command in the create menu, and it allows you to essentially create a copy of connectors or domains through either a translation or a rotation. Once you define the translation or rotation and you save the new periodic copies, then you end up with a set of connectors or domains that are essentially tied to each other from that point on. And so any changes made to one automatically apply to the periodic pair. All right, let's go through and look at this. We have an example. It's essentially the same geometry, except we're going to work on this periodic set of surfaces that we have here to the right. Again, the same defaults that we saw. We're going to create some domains here on these surfaces, and then we'll go through and create our periodic copies of those. So let me switch back over here to pointwise. We already have our defaults set up, the same ones that we used in the last example. So I just need to select these database surfaces. I'm just going to use a box, hold the control key, create my domains. So I have my new domains created. I can come over to the list and just click on the header for domains after I change my mask to select all three of them. And then I'll go to the create menu, periodic, and rotate. I have a couple of things that I need to set up here. So we're in the rotate, periodic rotate command. So the primary two things that I need to set up are the axis that I'm going to rotate about. And in this example, it's pretty simple. I can just rotate about the x-axis. So I'll do a point and direction for that. And then the angle that I want to sweep it through. And the angle is 8.78 degrees for this case. So back to pointwise. I'll go ahead and type in the angle and do point and direction, the origin. And as soon as I hit enter, it defines the axis, it rotates the domains. And so these are going to be my new periodic copies. So I had selected 3 domains, so I'm actually going to create 3 new domains that are periodically tied to the original ones. So that's really all I need to do. I'll just click OK, have a new periodic set. These are not purple because they do not lie on database surfaces, so they're not being parametrically initialized, but they should match the original set. If we look in the list panel and expand our domain list, you will see that we have these specially denoted in here as periodic sets. So domain 1 is periodically tied to domain 4. One of the slides that I skipped over talked about redimensioning these domains because my default dimension was 101, and so these 2 little narrow domains on the sides have 101 points spanning across them, which is probably a lot more than we really need in those particular cases. So let's just go to grid dimension and change these real quick. So maybe 41 points here. And this one's a little more narrow, so let's make this one 31 dimension. And OK. And so as soon as I made those changes, these are updated as well, because they're tied periodically. I can also come in, for instance, and take this domain and split it. And the periodic domain splits as well. So all the changes made to one should automatically be made to the other. And this next slide just shows the list, as I mentioned, and the fact that the names of the domains in the list do show that they're periodically tied